There's a point in every great journey where the traveler passes through a threshold that can never be crossed back over. A place where everything behind and everything ahead become entirely different environments, and the simple act of moving through that line changes the nature of the journey itself. For Voyager 2, that moment came on November 5th, 2018, roughly 11 billion miles from Earth. On one side of that invisible line lay the sun, its wind, its magnetic field, its charged particles, its protective reach. On the other side lay something no instrument had ever measured directly from within before. The true interstellar medium, the plasma that exists between stars, the ancient environment beyond our sun's control. Voyager 2 crossed that line, what it discovered on the far side, and was so unlike what the models had forecast that 5 different teams of scientists felt the need to publish 5 separate papers on the very same day, exactly 1 year after the crossing, just to explain what they'd found. This isn't a tale about some unsolvable mystery. It's a story about a boundary that outer solar system physicists had theorized about for decades, believed they understood, and that a single spacecraft revealed they'd gotten substantially wrong. And the consequences of that error stretch back across 11 billion miles of space, all the way to the shield that makes life on Earth possible, and to questions about how dependable that shield really is across long stretches of time. I am Your Name, and this is your channel. Subscribe now for more stories like this one. We dig this deep into real science every week. Now let's begin at the start, because to grasp what Voyager 2 found at the outer edge of our solar system, you first need to understand what that edge actually is, and why reaching it took 41 years. Most people picture the solar system as ending somewhere near Pluto. That's an understandable assumption, given how the solar system is usually shown in textbooks and documentaries. Pluto was the farthest known planet for decades, and diagrams tend to stop around there. But in a strict physical sense, Pluto isn't the edge of the solar system at all. It orbits well within a region still firmly under the sun's control. The genuine boundary of the solar system, the point where the sun's influence truly stops and something else takes over, is a completely different kind of structure, and it lies far, far beyond Pluto. The sun doesn't just give off light and heat. It constantly emits a stream of charged particles known as the solar wind, blasting outward in all directions at several hundred kilometers per second. This solar wind pushes against the surrounding space and blows up a massive bubble that surrounds our entire planetary system. That bubble is the Heliosphere. Within it, the sun's magnetic field rules. Within it, the solar wind is the dominant particle environment. Within it, everything from Mercury out past Pluto exists inside a continuous flow of material that came from our star. The outer edge of this bubble is called the Heliopause, the point where the solar wind finally loses its energy and is halted by the interstellar medium pushing back from the opposite direction. Past the Heliopause, there's no more solar wind. The magnetic environment belongs to the galaxy, not the sun. The particles there aren't solar particles. It's a fundamentally different physical environment from anything found inside the heliosphere. To cross the Heliopause is to genuinely leave the bubble our star constructed and step into the galaxy itself. It took Voyager 41 years to reach that boundary. Launched in August 1977, it flew past Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989, and then kept going. Over the following 3 decades, it continued outward, gradually losing speed to the sun's gravity, but still moving fast enough, over 40,000 kilometers per hour at points, to keep advancing toward the heliosphere's outer limits. Then, on November 5th, 2018, its instruments picked up the unmistakable signal that it had crossed the Heliopause. Solar wind plasma readings dropped to nearly nothing. Galactic cosmic rays spiked. The character of the magnetic field shifted. In under a single day of travel, Voyager 2 had moved from one physical environment straight into another. It became only the second spacecraft ever to reach interstellar space. Voyager 1 got there first, crossing the Heliopause in August 2012 from a different direction. But here's where the story becomes genuinely significant, and why Voyager 2's crossing produced 5 simultaneous papers, while Voyager 1's crossing, 6 years prior, had left major questions open. When Voyager 1 crossed in 2012, it did so with a damaged set of instruments. Its plasma science instrument, the device built specifically to measure the plasma around it, had failed back in 1980. By the time Voyager 1 reached the Heliopause, that instrument had been dead for 32 years. Researchers could still study the crossing using the magnetometer, cosmic ray detectors, and other tools, and they learned plenty from those. But the clearest direct view into what the plasma itself was doing on either side of the boundary simply wasn't available. Scientists had to estimate plasma conditions from indirect readings, leaving some of the most basic questions about the Heliopause crossing unresolved. Voyager 2's plasma instrument, on the other hand, was still functioning. Given that this was a spacecraft over 41 years old operating amid the radiation of the outer solar system, that was almost miraculous. Built in the 1970s, the instrument had run nearly continuously for over 4 decades. When Voyager 2 reached the Heliopause in November 2018, it was ready and working. For the first time ever, scientists had a spacecraft crossing the Heliopause equipped with a functioning plasma instrument, able to directly measure the temperature, density, and velocity of plasma on both sides of the boundary as the crossing unfolded in real time. What it recorded reshaped the picture in ways that took 5 research teams a full year to work through before publishing. The first surprise involved the Heliopause itself. For decades, theoretical models of the Heliosphere predicted that the transition between solar wind and interstellar medium would be a broad, gradual zone, the solar wind slowing and thinning out over a considerable distance before giving way to interstellar plasma, the two environments blending together the way 2 rivers merge rather than meeting at a sharp edge. What Voyager 2's plasma instrument actually recorded was strikingly different. The crossing took less than a day. On November 4th, 2018, Voyager 2 was still in the heliosheath, the heliosphere's outermost layer. By November 5th, it was in the interstellar medium. The shift between the two environments wasn't a slow fade. At the scale the instruments could measure, it was essentially a hard line, a boundary so narrow and so sudden that the spacecraft crossed it within a single day, with plasma unmistakably solar on one side and unmistakably interstellar on the other. The paper detailing the plasma instrument's findings, published in Nature Astronomy in November 2019, placed the width of the actual transition layer at under 0.06 astronomical units. 1 astronomical unit equals the distance from Earth to the Sun, roughly 93 million miles. Less than 6% of that distance for the entire transition. On the scale space physics normally works at, where distances run into the millions and billions of miles, that's an extraordinarily thin boundary. No model had predicted a transition this abrupt. The second surprise came from the temperature of the interstellar plasma beyond the boundary. Models had forecast that the interstellar medium near the Heliopause would be cold, significantly colder than what the plasma instrument actually recorded. The interstellar plasma outside the heliosphere turned out to be hotter than predicted. Not dramatically hotter in raw numbers, but measurably hotter relative to what decades of theory had anticipated. The same paper noted that the very local interstellar medium, the specific patch of interstellar space immediately surrounding our heliosphere, varies near the Heliopause, meaning its properties shift as you move through it. The quiet, cold, uniform void everyone expected turned out to be neither as cold nor as uniform as the models claimed. The third finding came from magnetometer readings, published in a separate Nature Astronomy paper analyzing Voyager 2's magnetic field data through the crossing. Just inside the Heliopause, within the heliosheath, the magnetic instrument detected what researchers call a magnetic barrier, a zone where field intensity jumps sharply above typical heliosheath levels, forming a layer of elevated magnetic pressure between the bulk of the heliosphere and the Heliopause itself. Voyager 1's magnetometer data had partially hinted at this barrier during its 2012 crossing, but Voyager 2's crossing confirmed it far more clearly and added detail on how it interacts with cosmic rays entering the heliosphere from interstellar space. Cosmic rays are among the most energetic particles in existence, born from supernovae and other violent cosmic events, streaming through interstellar space near the speed of light. The heliosphere partially shields the inner solar system from them, lowering the intensity of cosmic radiation that reaches the planets. That shielding, it turns out, works in part through this magnetic barrier that Voyager 2 detected. The barrier's magnetic pressure impedes the inward movement of cosmic rays, deflecting or slowing them before they can penetrate further into the heliosphere. This is a real, measurable effect with genuine consequences for the radiation environment of the inner solar system, Earth included, and no model built before Voyager 2's crossing had correctly described how it actually functions. The fourth finding emerged from comparing Voyager 2's measurements against Voyager 1's from 6 years earlier, and it may be the most conceptually important result of the entire crossing. The 2 probes crossed the Heliopause at different locations, heading in different directions relative to the solar system's orientation within the galaxy. Voyager 1 crossed in the northern solar hemisphere, heading roughly toward the nose of the heliosphere, the direction the sun moves through the galaxy, where the solar wind pushes hardest against the interstellar medium. Voyager 2 crossed in the southern solar hemisphere, heading more toward the flank, a different part of the boundary entirely. If the heliosphere were a perfectly symmetric sphere with identical properties in every direction, both crossings should have revealed roughly the same conditions at the Heliopause. They didn't. Voyager 2 found a thinner boundary than Voyager 1 had, along with stronger interstellar magnetic fields and different plasma conditions. Both probes located the Heliopause at roughly the same distance from the Sun, about 120 astronomical units, which was itself somewhat unexpected, given that the 2 crossings happened under different solar activity conditions. But the nature of the boundary itself differed between the two locations. The heliosphere isn't a perfect sphere. Its shape and symmetry are shaped by the direction the sun travels through the galaxy and by how the interstellar medium flows around it. The two Voyager crossings at different points along this uneven surface measure different things because the surface itself differs from place to place. This asymmetry matters for a specific reason researchers have started exploring since the crossing data came out. If the heliosphere is asymmetric, compressed on one side, stretched out on the other, then the thickness and strength of the protective barrier against cosmic radiation also varies with direction. The inner solar system isn't shielded equally on all sides. The amount of cosmic radiation reaching Earth from different parts of the sky may be subtly shaped by the heliosphere's geometry, and that geometry is itself shaped by the interstellar environment surrounding it. The two data points from the Voyager crossings, one from the nose, one from the flank, are the only direct measurements we have of this shape from the inside, and they're producing models of heliosphere structure that look noticeably different from the symmetric sphere most people were taught about before 2019. The fifth major finding concerned what the interstellar magnetic field is actually doing near the heliopause. For decades before either Voyager reached the boundary, physicists predicted that the galactic magnetic field outside and the solar magnetic field inside would be largely separate. Two distinct magnetic environments meeting at the heliopause with limited interaction between them. What both Voyager 1 and Voyager 2 found at the boundary was that the relationship between the two is far more complex and interconnected than the model suggested. The galactic magnetic field outside is stronger than expected, 2 to 3 times the strength that the best pre-crossing models predicted. This stronger field pushes on the heliosphere with considerably more force than anyone had calculated. Independent estimates, based on the Voyager data, suggest interstellar particles pressing against the heliosphere from outside exert up to 10 times the pressure earlier models assumed. That's not just an abstract figure. The pressure the interstellar medium places on the heliosphere partly determines its size and shape. A more compressed heliosphere might offer somewhat less protection to the inner solar system. Over geological timescales, if the sun travels through regions of the galaxy where the interstellar medium is denser or more magnetically active than our current surroundings, the heliosphere could be compressed enough to expose the inner solar system to higher cosmic ray levels than we experience now. The Voyager data doesn't prove this has happened or will happen on any particular timeline, but it does confirm the interstellar medium presses on the heliosphere with more force than the models accounted for, which changes the baseline for how stable and consistent the heliosphere's protection really is. All 5 findings, the sharp boundary, the hotter interstellar plasma, the magnetic barrier, the asymmetric heliosphere shape, and the stronger interstellar magnetic field and pressure, were released to the scientific community together on November 4th, 2019, exactly 1 year after the crossing, in 5 papers published simultaneously in Nature Astronomy. That simultaneous release was intentional. The findings from Voyager 2's various instrument teams were interconnected, each adding context to the others, and releasing them all at once let the wider scientific community absorb the complete picture immediately, rather than piecing it together over months or years. The response within the astrophysics and heliophysics communities wasn't alarm, but it was a serious recalibration. Patrick Cohn, a heliophysics program scientist at NASA headquarters, described Voyager 2 as the first platform to genuinely experience the interstellar medium from within, calling it, quite literally, a pathfinder. That word was chosen carefully, not for dramatic effect, but because it's accurate. There was no path before this. There were only models built from observations taken deep inside the heliosphere and theoretical guesses about what lay beyond. And those models, however sophisticated, missed the sharpness of the boundary, the plasma's temperature, the magnetic field's intensity, and the heliosphere's asymmetry. A pathfinder goes somewhere first and returns with information that redraws the map. Voyager 2 isn't coming back, but the data it sent home rewrote every map that mattered. Now consider what this means for the 2 instruments Voyager 2 still has running in interstellar space today, more than 7 years after the crossing. The heliosphere boundary wasn't the end of the story, it was the start of a new chapter. The interstellar medium Voyager 2 entered on November 5th, 2018, isn't a uniform, quiet backdrop. It has structure, it has turbulence. The plasma within it shifts in density and temperature as the spacecraft moves through it. Compression waves triggered by solar eruptions, powerful enough to send shock waves all the way past the heliopause into interstellar space, have been picked up by Voyager 2's instruments from outside the heliosphere, proving that the 2 environments are linked in ways beyond the static boundary the pre-crossing models described. The heliosphere, in a sense, breathes, responding to solar activity and to the pressure of the interstellar medium, and Voyager 2 has been tracking that breathing from outside since late 2018. Each passing year brings the spacecraft closer to the point where its power supply can no longer run its instruments. Each year, the team at JPL faces tougher calls about which instruments stay on and which get shut down. The plasma science instrument that made such a thorough record of the Heliopause crossing is still running, but it's aboard a spacecraft losing roughly 4 watts of power annually and can't operate forever. The window for direct plasma measurements from the southern interstellar medium is limited. Once it closes, there's no replacement instrument on any current trajectory to take its place, and no mission to do so has been funded, designed, or approved. What Voyager 2 crossed on November 5, 2018, was the edge of everything our sun ever built. Everything within its protective reach, everything our civilization has ever, in any physical sense, called home. On the other side of that edge, it found a universe hotter than expected, more magnetically active than predicted, pressing harder against our solar system than any model had calculated, bounded by a line thinner and sharper than anyone had anticipated. The textbook image of the Heliosphere, a smooth, symmetric sphere fading gently into quiet interstellar space, had to be redrawn. 5 teams of scientists published 5 papers on the same day to begin that process. And the spacecraft, responsible for all of it, is still out there right now, still moving deeper into interstellar space, still measuring, still transmitting, still doing exactly what it was built to do a decade before most of the scientists studying its data today were even born. If you come here for real, verified, world-changing science, subscribe now, turn on notifications, and drop a comment below with the space mystery you'd like us to cover next. Share this with someone who should be watching, because this is the kind of story that deserves a much bigger audience than it gets. Thanks for watching. Let's go deeper into one particular finding from the crossing, because it's the one that most directly ties what Voyager 2 measured 11 billion miles away to questions about life here on Earth. And it's the finding the 5 Nature Astronomy papers together addressed most carefully without any single one fully resolving it. The heliosphere isn't just a fascinating scientific structure. It's what makes the inner solar system livable. Cosmic rays, the ultra-high energy particles born from supernovae and other violent galactic events, constantly stream through interstellar space. Without the heliosphere to partially deflect and slow them, the inner solar system would face significantly higher cosmic ray levels than it currently does. Research suggests that prolonged exposure to elevated cosmic ray levels could raise mutation rates in living organisms, alter atmospheric chemistry, and potentially affect climate. The heliosphere isn't merely a line on a diagram. It's part of the reason biological evolution on Earth unfolded the way it did. The question the Voyager data raises, not alarming but serious enough that researchers are actively pursuing it, is how stable and reliable that protection truly is. The answer hinges on 2 main variables. The first is the state of the interstellar medium surrounding the heliosphere. If the heliosphere passes through a denser or more magnetically active patch of interstellar space, it gets compressed, and a compressed heliosphere offers less shielding than a larger one. The second variable is the sun's own activity level, which controls how much solar wind the heliosphere has to work with. A more active sun generates more solar wind, supporting a larger heliosphere. A quieter period produces less wind, letting the heliosphere shrink. What Voyager 2's crossing data revealed is that interstellar magnetic pressure on the heliosphere runs roughly 10 times higher than pre-crossing models assumed. That greater external pressure means the heliosphere is being squeezed more than predicted, making it somewhat smaller than the models claimed. This isn't a crisis. The heliosphere remains more than large enough to offer substantial protection to the inner solar system. But it does mean our models of exactly how much protection we have and how that protection shifts over geological timescales as the sun moves through different regions of the galaxy need to be recalculated using real numbers that only Voyager 2 was positioned to supply. That recalibration is still underway. Papers published since the 2019 crossing analysis have continued refining our understanding of the heliosphere's shape, its reaction to changes in solar activity, and the structure of the very local interstellar medium surrounding it. Each of those papers draws, in part, on Voyager 2's ongoing stream of data from within interstellar space. The spacecraft that crossed the Heliopause in 2018 is still contributing to the scientific analysis of that very crossing, because the data it continues sending back about the interstellar medium. It's traveling through adds ongoing context to what happened at the boundary itself. Consider what that continuous data stream actually represents. Since November 2018, Voyager 2 has sent back measurements from inside the interstellar medium every single day, plasma density readings, magnetic field strength and direction, particle counts from both solar and galactic sources. In a very real sense, the spacecraft is drawing a map. Not a map of geographic features, the way a surface probe maps a planet, but a map of conditions, a record of what the interstellar medium near our solar system looks like as a function of distance from the heliopause, built point by point as the spacecraft pushes deeper into it. No such map existed before November 5th, 2018. No telescope on Earth can replace it, and it can only continue as long as the spacecraft keeps operating. The 2023 communication blackout, which lasted 14 days before the Canberra station managed to restore contact, interrupted that mapping process for 2 weeks. 14 days of data points now lost forever. Within the scope of a mission spanning decades, 14 missing data points is a small gap. But every gap in the record covers a section of the map that can never be filled in later, since the spacecraft passes through each point in space only once. Whatever conditions existed during that 14-day window, in that particular stretch of interstellar space, at that particular distance from the Heliopause, was recorded by instruments that weren't communicating with anyone on Earth for 2 weeks. That data is gone for good. The larger gap, when it eventually arrives, will be permanent and complete. Once Voyager 2 loses power and falls silent, the map ends exactly where it stopped. Whatever lies beyond in the very local interstellar medium, whatever shifts occur in plasma density, magnetic field strength, or cosmic ray intensity at greater distances from the heliopause, will remain unknown until something else reaches those distances. And right now, nothing else is headed there. There's one final piece of what Voyager 2 found at the heliopause crossing worth including here, because it shifts the story from physics into something harder to define but no less real. Both Voyager 1 and Voyager 2 reached the heliopause at roughly the same distance from the Sun, about 120 astronomical units, despite crossing at different times and under different solar activity conditions. Scientists found this unexpected. The size of the heliosphere was thought to fluctuate significantly with the solar cycle, the roughly 11-year rhythm of rising and falling solar activity that governs sunspot counts and flare frequency. At solar maximum, the Sun produces more solar wind, which should push the heliopause outward. At solar minimum, less solar wind should let it contract inward. Voyager 1 crossed during a period of relatively low solar activity. Voyager 2 crossed during relatively high activity. Scientists expected them to find the heliopause at meaningfully different distances. They didn't. This suggests the interstellar medium's pressure stays stable enough over the relevant timescales to keep the heliopause at roughly the same location, regardless of where the Sun sits in its activity cycle. In other words, the external environment plays a bigger role in setting the heliosphere's size than the internal solar wind alone. The galaxy pushes back, and it does so with enough consistency to hold the boundary nearly steady. There's something meaningful in that, in the image of our Sun straining to maintain its bubble against the galaxy's constant outside pressure, and the galaxy holding that boundary nearly fixed, no matter what the Sun does internally. It's a relationship between our star and its galactic surroundings that our models had gotten wrong, one that a 41-year-old spacecraft, still running on hardware built before home computers existed, measured directly for the first time on a November day in 2018. That spacecraft is farther from Earth today than it was then. Its power supply is smaller, its instrument count is lower, but its remaining instruments are still gathering data from within the interstellar medium, still building the map that starts at the heliopause crossing and extends outward into space. No model has ever correctly described from first principles, and no mission besides Voyager 2 has ever measured directly from the inside. Subscribe now to keep following the story. Leave a comment telling us which discovery from this video surprised you the most, and share this with someone who should know that the most important scientific data about the edge of our solar system is being collected right now by a machine built before most of the people watching this were even born.